Hello and welcome to this video lesson. This is the fourth video lesson in the energetics series, and now we're going to study Hess's law, as mentioned in one of the previous lessons on calculating molar enthalpy changes. This is an alternative way of calculating molar enthalpy changes, and it has specification reference 3.1.4.3. So first of all, let's have a look at our lesson objectives. And we want to understand Hess's law, obviously, what it is. But then, of course, we want to be able to use Hess's law to perform calculations, including the calculation of enthalpy changes for reactions, using enthalpy changes of combustion, or for example, to calculate enthalpy changes for reactions from enthalpy changes of formation. So just to make those clear, let's say enthalpy changes for reactions, that's written like this. So we'd calculate enthalpy changes for reactions from enthalpy changes of combustion or enthalpy changes of formation. So any sort of combination of the three, to be honest. You might be given one and asked to calculate another. So there's our lesson objectives. First of all, let's look at what is Hess's law. First of all, who was Hess? This was Germain Hess. He was a Russian chemist, studied in Sweden and worked as a doctor most of his life. And anyway, he came up with Hess's law, which says the following. Hess's law says that the total enthalpy change for a reaction is independent of the route taken. So that doesn't mean much, I don't think, as it stands. So let's have a look at an example to illuminate it. So let's have a look at an example of nitrogen dioxide. So let's say you have some nitrogen dioxide gas, and you're going to decompose that. So you're going to decompose that into its components, so nitrogen gas and oxygen gas. Well, first of all, we need to balance this. So we need 2 moles of nitrogen dioxide, and that gives us 1 mole of nitrogen and 2 moles of oxygen, like that. So now that's balanced. So let's say we wanted the enthalpy change for that reaction there, that decomposition reaction. That is actually a very difficult reaction to do in the lab and to measure, and we'd struggle to work out that that enthalpy change. Let's call that route 1. Let's call that route 1. And so instead of going along route 1 to directly decompose the nitrogen dioxide into nitrogen and oxygen, because that's difficult, we might choose a different route. So we might first partially decompose the nitrogen dioxide into 2 moles of nitrogen monoxide. That would be a gas, and of course we'd have some oxygen as well. And once we've got that partial decomposition, we can do the second step, which would get from the nitrogen monoxide and oxygen to the nitrogen and oxygen. So let's call the combination of these 2 steps route 2. So I'll write route 2 down here. So what Hess has said is that to get from, and I'll write this in green, to get from, let's say, reactants to products, it doesn't matter whether you go via route 1 or route 2. The enthalpy change is going to be the same. So that's in principle what Hess's law says. Let's have a look at some numbers just to make it clearer. So if we were to do the reaction where we partially decompose the nitrogen dioxide, so we've got some nitrogen monoxide to oxygen, that's the first step of route 2. We can do that in the lab, and we could measure that, and when people have measured that, they've found that that's an endothermic reaction, and per mole you're getting 114 kilojoules when you do that reaction there. And the second step, going from the nitrogen monoxide and oxygen through to the nitrogen and more oxygen, when you do that in the lab, you find that that's an exothermic reaction. It's an exothermic reaction to the tune of 180.8 kilojoules per mole. Right, so if we're able to do those two steps in the lab, then we can use that information in order to find out the enthalpy change for the original route 1 reaction. And so what that turns out to be, we can see delta HR standard, and it doesn't really matter whether I put my R here or after the delta sign. We can say that that is following the arrows along. So we add the individual enthalpy changes of route 2. We add them in the direction of the arrows. So we start with 114. That should have been 114.4 to be honest. So 114.4 for the first step of route 2. So we followed the arrow first, and then we're going to add the enthalpy change for step 2 of route 2, and we find that that is minus 180.8, and that turns out to be minus 66.4 kilojoules. So there's Hess's law. So we've gone through a two-step route 2 process and added our two enthalpy changes together to equivalate what the enthalpy change would be for one-step route 1 enthalpy change would be if we were able to do it. So there is our answer, and that illustrates Hess's law. So what we're going to do now is have a look at an example, and the example is going to be finding the enthalpy change for a reaction using enthalpy change of formation information. Yeah, so let's write that like this. So we're going to use enthalpies of formation. So that's the data that we're going to refer to, and we're going to use that data to calculate an enthalpy of a particular reaction. And so let us write down the reaction. So we want to calculate. This is our question. We're going to calculate the enthalpy change of reaction at standard conditions for this reaction. Yeah, we're going to take some sulfur dioxide, which at standard conditions is a gas, and we're going to react that with 2 moles of hydrogen sulfide, also a gas, and that would make some sulfur, which at standard conditions is a solid, and it would also net you off 2 moles of water. Just write that down here, 2 moles of water, which would be a liquid. Okay, so that's our exam question. We're going to calculate that enthalpy change of reaction for the reaction that I've written out there in blue. And what you would do to start with is you'd write a nice little triangle with reactants, products and elements in it. So let's do that. Let's change colour and do that in green. Okay, so on the left we're going to have reactants, and then over here we'll have products, and right down here we'll have elements. Because you'll remember that enthalpies of formation is taking elements and from them making compounds. Okay, so our Hess's law triangle is going to be a triangle including reactants, products and elements. So in this case our reactants are sulfur dioxide and hydrogen sulfide. And they give us our products, which are sulfur and water. Okay, so that's our reaction, just written down in a slightly different format. And what we then do is we're going to split those reactants into the elements and write them down below. And they will be the same elements that make up the products as well. So if you look at the reactants, you've got sulfur dioxide and you've got hydrogen sulfide there in those molar quantities. You see that you have 3 atoms of sulfur. So you've got 3 atoms of sulfur. And then looking at the hydrogen, you see you've got 4 atoms of hydrogen there. But at standard conditions, those 4 atoms of hydrogen are going to exist as hydrogen gas. So you can have 2 moles of hydrogen gas. And in those reactants, you also have 2 atoms of oxygen. And the same applies to the oxygen, that will exist as an oxygen molecule. Written like that. Okay, so we can go from our elements that we've written down to our reactants, all right? Or we could also alternatively make the products. You'll notice if you spend some time just looking at those elements, you'll see that those elements make the products in the right quantities, and they also make the reactants. Okay, so we could list that as we could call this left-hand arrow, we could call that the enthalpy change of formation of the reactants. And in the same way, we could call this right-hand arrow the enthalpy change of formation of the products, like so. So that's our Hess's law triangle, and if we want the enthalpy change of reaction there, we can't do that very easily directly, so we're going to use some data, some enthalpy change of formation data, in order to do that. So here is the data. Scientists have done these formation reactants. They've made sulfur dioxide and hydrogen sulfide out of the elements, and they've also made water out of its elements as well. And the results are in this table that you see in the top right hand corner. So we can use that data to work out first the enthalpy change of formation of the reactants that we wrote down on the left, and then we can use that data in the table to work out the enthalpy change of formation of the products. And once we have those 2 pieces of information, then we can use those 2 bits of data to work out our enthalpy change of reaction, which is what the question is telling us to do. Okay, so let's start at the start. Let's work out the enthalpy change of formation of the reactants. So let's do that in green still, shall we? So we've got the enthalpy change of formation of the reactants. That's what we're going to do first. And so looking at the elements, you've got 3 atoms of sulfur, 2 molecules of hydrogen, 1 molecule of oxygen, and with that you're going to make 1 molecule of sulfur dioxide. And so from this line of the table, you can see that to make 1 mole of sulfur dioxide, it's going to cost you, it's going to actually give out 297 kilojoules of energy. Okay, so we're going to write our minus 297 here first, and so now we've made our sulfur dioxide, we've made our 1 mole of sulfur dioxide. But we also need to make 2 moles of hydrogen sulfide. So we're going to look at hydrogen sulfide, which is the middle row of the column. And to make 1 mole of hydrogen sulfide is going to give out minus 20.6, but we've got 2 of them, so we have to multiply that by 2. And so when we do that calculation, we're going to find that the answer is minus 338.2 kilojoules per mole. All right, so let's just take that number and write it on Hess's law. So let's take minus 338.2 and put it there, and then switch back to green. So now what we're going to do is work out the enthalpy change of formation of the products. First thing is, one of the products is sulfur solid, which is an element. So there's no enthalpy change when elements are made from elements. So for completeness, we can put that down as 0. You could even put 3 times 0 if you want. So that takes care of the sulfur. But we're also making 2 moles of water. Right? So we need to use the 3rd row of the table here. So when 1 mole of water is formed from its elements, then we that's exothermic, and we're getting out 286 kilojoules of energy. But we're going to use 2. We're making 2 moles, so we're going to write it like this. Okay, so 2 times 286 is 572, so that comes out at minus 572 kilojoules per mole. Okay, so in the same as we did before, let's write that on our, we call it a thermocycle, so it's minus 572. So now we're ready to actually answer the question, which is to calculate the enthalpy change of reaction for the above reaction, which is this one that I've just underlined here. So what we're going to do is we're going to use the root 2 via the elements, but the first thing you'll notice is that when you go from the reactants to the elements, you're going against the direction of the arrow. You're going against the direction of the arrow. So instead of, so what you do when you're going against the direction of the arrow is you just reverse the sign of the energy change there. Okay, so we're going to take the minus 338.2 and we're going to make that into 338.2, positive 338.2. So that gets us down to the elements, and now we're going to add that to the enthalpy change of formation of the products. So we're going with the direction of the arrow. So in purple I've just illustrated that we're going with the direction of the arrow, so then we're able to add the energy change, but of course we're adding a negative number, so we'll write it like this. Okay, so that is root 2, positive 338.2 plus a minus 572 kilojoules, and we work that out, and that comes out at 233.8 minus 233.8 according to my calculator, and that of course is in kilojoules per mole. And there is the answer to our question, which was up here: calculate the enthalpy change of reaction for that reaction. And we have done so. Hope that's been clear. We will have to look at another couple of examples, I guess, before you can do that from scratch on your own. But we will do so. So in that last example, we used enthalpy changes of formation. And what we're going to do now is we're going to use enthalpy changes of combustion. So we're going to use enthalpy changes of combustion, and we're going to use them to find out, let's say, enthalpy changes of formation. So here, let's start this time by looking at some enthalpy changes of combustion. So we've got carbon. When we combust carbon, 1 mole of carbon, we're going to get 394 kilojoules. When we combust 1 mole of hydrogen gas, we're going to get 286 kilojoules given off. And there we have the enthalpy change of combustion for ethanol at an exothermic 1367 kilojoules. So let's say our question is this. Let's say our question is, we've got to calculate the enthalpy change of formation, standard conditions, of ethanol. And we have to use these enthalpy change of combustion data. So the first thing we want to do is we want to write down our equation. So let's write it down in the same format as we did before, with reactants and product. In this case, it's one product, which of course is ethanol. But in this case, what we're going to have at the bottom are combustion products. Now, because we're using enthalpies of combustion. Alright, so if our product is ethanol, that's the one we're interested in. Ethanol is C2H5OH, as is given there. And if we are going to form that, we would form it out of the 2 atoms of carbon, which at standard conditions is going to be solid. And actually, I didn't put our state symbol in for our ethanol, which of course is liquid at standard conditions. So 1 mole of ethanol is made up of 2 atoms of carbon and 3 moles of hydrogen gas, and also 1 atom or half a mole of oxygen gas. So that would be our delta H of formation. So let's write that in a different colour, because what we've written along the top is what we want. That's what the question is asking us for. That enthalpy change that I've written in green there. That's what we want. But we've not been given formation data, we've been given combustion data. So if we take those reactants, those elements, and we combust them, then we would come down in this direction. And our combustion products, if you combust carbon, you're going to get carbon dioxide, and you've got 2 atoms of carbon, so you're going to have 2. So you've got 2 moles of carbon, so you're going to get 2 moles of carbon dioxide. Given off. And if you combust 3 moles of hydrogen gas, you're going to get 3 moles of water, which at standard conditions is a liquid. And they are our combustion products. The combustion products are always assuming complete combustion, and they're always carbon dioxide and water. So there are combustion products when we combust our reactants. But of course we can also, before we go on to the other step, let's just add our oxygen in there, because what we're going to do is add our oxygen. So we need, how many moles of oxygen did we need to combust those reactants? Well, we needed 3 moles of oxygen gas to combust those 2 moles of carbon and 3 moles of hydrogen. Alright, so we've combusted our reactants now. The next thing we want to do is we want to combust our product. So if we combust our product, you're also going to get, you've got 2 atoms of carbon in one molecule of ethanol, so you're going to get 2 atoms of carbon dioxide out of it. You've got 6 hydrogens there, so you're going to get 3 moles of water. So again, what we're going to do here is we're going to write down our 3 moles of oxygen gas that we're going to need if we burnt 1 mole of ethanol. So let's just label these legs of the thermocycle as we did before. This one is the enthalpy change of combustion of the reactants. And this one here is our enthalpy change of combustion of our product. Okay, so if we work out those 2 steps, which we've annotated in red just now, then we would be able to work out the enthalpy change of formation of ethanol, as we've annotated in green there. So let's do that in sequence. Okay, so let's start off with our enthalpy change of combustion of our reactants. Okay, so we are burning 2 moles of carbon to get 2 moles of carbon dioxide. So we're going to use this first line here. So when that tells us that when we burn 1 mole of carbon, that's exothermic to the tune of 394 kilojoules. But we're burning 2 moles of carbon, so we're going to have to multiply that by 2. Okay, that's carbon taken care of, and the hydrogen, we're burning 3 moles of hydrogen gas, so we're going to use the middle row here, and we're burning 3 moles of it, so we're going to multiply by 3 the value for hydrogen gas, which is minus 286. And let's plug that into a calculator and see what we get. And what we get is minus 1,646 kilojoules per mole. And in the same way, let's do our enthalpy change of combustion for our product, ethanol. Okay, and we've got 1 mole of that being burnt. So we're going to just take the minus 1,367. That is in the table on the 3rd row, just like that. So now we can, for sake of completeness, let's just write those numbers in here. So we're going to put the minus 1646 in there, and we'll write our minus 1,367 in there. Okay, and that leaves us able to work out our answer. So in principle, what we're going to do is we're going to say the enthalpy change of formation, under standard condition of ethanol, equals the enthalpy change of combustion of our reactants. Alright, so we've left that symbol unchanged because we're going in the direction of the arrow. But from the combustion products up to the product, we're going against the root of the arrow, so we're going to say it's minus the enthalpy change of combustion of our product. Okay, so putting the numbers into that equation, so our enthalpy change of reactants is minus 1646, and that we're going to subtract from that our enthalpy change of combustion of our product, which is minus 1367. And if we put that into our calculator, we will get minus 279 kilojoules per mole. And that is our answer to the question which we were asked right at the top here. What is the enthalpy change of formation of ethanol? Well, the answer is an exothermic 279 kilojoules per mole. Thank you very much. Okay, so before we finish, let's make sure we've covered off our learning objectives. Do we understand Hess's law? Well, Hess's law is that if you want to go from reactants A to products B, it doesn't matter whether you go directly from A to B or you go via intermediaries like C. It doesn't matter what route you take, you will find the same enthalpy change overall. And so that is Hess's law. Hopefully we understand that. And then after we understood Hess's law, we used data to perform calculations. First of all, to calculate an enthalpy change of reaction using enthalpy change of formation data. And then we used enthalpy change of combustion data to get enthalpy change of formation information. So we did those two worked examples and performed those two calculations. So hopefully you've understood that. If not, re-look at the video or come and see me. Anyway, I'll see you soon.